Here I have a parallel circuit. There's a 9-volt cell and a 2K and a 1K resistor in parallel to the 9-volt cell. What do I mean by in parallel? We can see that all the charge has to flow through the main part of the circuit, out of the positive terminal of the cell, but then at this point, some charges go through the 2K resistor and others go through the 1K resistor. They then join again and all go back to the negative terminal of the cell. So there's a branch in the circuit. That's why we call it a parallel circuit. We can liken this parallel circuit to the picture that I've got here. Each blue circle stands for a group of moving charge, a coulomb of moving charge. So in the wires, in all the wires around in the circuit, there are many, many electrons, many charges. And the battery pushes these. Some of them can move. And those that move form what we call electric current. They are moving charge. And that's what I've shown here in the blue circles. You can see that some of these blue circles have many red lines, some have fewer, and some have no red lines. What do those red lines mean? Each red line stands for 1 joule of electrical energy. We must imagine these blue circles, these groups of charge, moving out of the positive terminal around the circuit, either through the 2K resistor or through the 1K resistor, joining back up again to go into the negative terminal of the cell. Can you see that as they move through the cell, they get given energy? The cell gives them electrical energy. They leave the cell with 9 joules per coulomb. 9 volts. They come back into the cell with no joules per coulomb, no volts, 0 volts. And that's an important rule about electricity. The voltage at the negative terminal is always 0 volts. That means that the charges have to lose all the energy which the cell gives them as they pass through the circuit. They may not come back to the cell with any energy. So of course, if each group of charge has 9 joules of energy when it leaves the positive terminal and it has to come back home to the negative with 0, what has to happen as the charges move through the circuit? They must lose their energy. They have to lose all of it. It's like if your mother had a rule that every day she gives you 9 rand and you have to come home with nothing. What would you have to do? You'd have to spend 9 rand every day. Where do you spend money? At a shop. In a similar way, in a circuit which has a 9-volt battery, the charges have to get rid of those 9 volts that the battery gives them. Where do charges get rid of voltage? Through resistors. In this parallel circuit, notice that each charge only goes through one resistor. None of the charges go through both of the resistors as they pass in one circuit around. Because at this point, they have to choose whether they go through that branch or that branch. Some go through the 2K resistor and others go through the 1K resistor. So since each one only goes through one resistor, each group of charge has to lose all its energy through that one resistor. So notice that in each case, the groups of charge come to the start of the resistor with 9 volt, and by the time they've finished going through the resistor, they have 0 volt, ready to go back home to the negative terminal. And that's why in this circuit, the voltage across the cell equals the voltage across branch 1, which equals the voltage across branch 2. That would be 9 volt in each case. The voltage across a component means the difference in voltage between the 2 points. So if we measure the voltage across the cell, the voltmeter will measure 0 volt at one terminal, at the negative terminal, and 9 volt at the positive terminal, and then it subtracts the 2. 9 minus 0 equals 9 volt. In that case, the meaning of that 9 volt is that the cell gives 9 volts. If we measure the voltage across the 2K resistor, the voltmeter measures 9 volt at the start of the resistor and 0 volt at the end. And then it subtracts the 2. 9 minus 0 equals 9 volt. And that's what the voltmeter reads, 9 volt. And the meaning of that 9 volts is that in between those 2 points, 9 volts has been lost out of the resistor. And if we measured the voltage across the 1K resistor, we would also find 9 volts. And again, that means that 9 volts has been lost as the charges move through that 1K resistor. Now let's speak about the current strength through various parts of the circuit. Current strength refers to how quickly the charges move, or more exactly, how many groups of charge move through a point per second. How many coulombs move through a point per second. We can understand this better by thinking about this circuit like having a very wide main road which splits into 2 roads. One road is just a single road, only one row of cars can drive on it. That's like the 2K resistor. Then the other road is like a wide road where 2 cars can drive next to one another. That's like the 1K resistor. So the main road, the main part of the circuit, splits into 2 branches, a narrow road and a wide road, a 2K resistor and a 1K. Now which road would more cars go on at the branch? The narrow road or the wide road? Of course the wide road, because more can fit next to one another there. And so it's easier to move. Double as many cars will go through the easy road than through the more difficult road in this case. In the same way, in this circuit, double as many charges choose the 1K path as the 2K. I've shown that by there being 3 rows of charge in the main part of the circuit, and then that splits. 1 row goes through the 2K resistor and 2 rows go through the 1K resistor. So double as many go through the 1K because it's double as easy. And then they join again in the main part of the circuit to go back together into the cell at the negative terminal. And we can write that in an equation. I main equals I1 plus I2. I stands for current strength. The current strength in the main part of the circuit splits into branch 1 and branch 2.